And without further ado, we'll get into our first presentation, Time Filter, Advanced Time Manipulation for Animators and Effects Artists. Here is Brent Forrest.
Thank you, Nora. All right. Hi, everybody. Good afternoon. My name is Brent Forrest, and I am the technical director at Marza Animation Planet in Tokyo, and I'm very happy to be here today to talk to you about the tool that we created at Marza called the Time Filter. Oops. All right, second try. So it's undeniable that the technology behind computer graphics has advanced and pushed the boundaries of filmmaking, but we have moved away somewhat from the fundamentals which make up the appeal of animation. And this is true in Japan, and it is also true in the West. So let's take a look at a little example here. This is a piece of animation that was done by Greg Court and assisted by Royston Robinson at a studio called Red Rover in Toronto about 20 years ago. Now, if we were to take into consideration the background painting and the digital ink and paint and compositing, these three scenes here would represent about $8,300 worth of work adjusted for inflation and would have taken about 2 weeks. Now, if you wanted to recreate this kind of work in CG, well, what would you need? Let's break it down. You're going to need a top-flight rigging and modeling team, I should say. You're going to need somebody on special effects. You're going to need somebody to handle your cloth, and because you can't get away from it these days, you're going to need hair and groom. Someone on sets and props, you need someone to light and render the thing. You need shading. You need compositing, you need delivery, and of course, you're going to need 1 or 2 animators. Now, this would represent significantly more than 2 weeks of work, and putting it all together, you're going to be looking at about $13,000, and that's not including the cost of software licenses. So today, I want to talk to you about a specific area of achieving the sought-after 2D style, and that's timing. That's putting your drawings on twos in 2D terminology, or as we say in CG, drop frame timing. Now, if you want to achieve this kind of style, it's important to know where it comes from. This is a dope sheet. A dope sheet is something that's been used in animation for close to 100 years. These annotations you see up here are how an animator communicates his intentions to the assistants and the camera operators down the pipe. This is the user's manual for constructing and shooting an animated scene, and all of this is written by the scene's animator. Here we can see an example of what we're talking about when we talk about drawings on twos and drawings on ones, and this is what that animation, what this sheet represents. The important thing here is that we only go on ones when it's absolutely required for very fast motion or for other reasons, which we'll get into later on. Now, if you were to look at the kind of timing that gets generated by standard CG, you'd get something that looks more like this. Everything on ones. There's no concept of anything but ones in standard CG, and there can't be. And this is one of the reasons why modern computer animation, modern CG, lacks the appeal of, say, a classic 1950s Goofy cartoon. But it's not the only reason. So here we have a walk cycle on twos, and if we were to drop a background behind this, well, one thing becomes apparent. We're going to have to do one of two things. We're going to have to either move the background or move the character to make the scene make sense. Okay, so the character is on twos, so let's move the background on twos. Now we have our first issue. When you move a background on twos, it becomes murder on the eyes, especially on the big screen. As a general rule of thumb, you don't want to be doing pans or camera moves of any kind on twos. So let's put the background on ones. Now we have a new problem. With the character who's animated on twos and a background moving on ones, you have slipping where the feet hit the contact plane. You'll have slipping when you have contact of any kind. So the animator has a couple of options to combat this. One of the things that you might see is you can frame in tighter, so you don't see where the feet touch the ground. Another solution might be to animate the character completely on ones, by far the animator's least favorite choice. Another option you might have is to split the animation into layers. You put the lower body on ones and keep the upper body on twos. So these are the kinds of decisions that animators and assistants make all the time. And that's the point that I'm trying to get at, is when you have these timing decisions to make, the timing decisions belong to the animator. That's the way it generally has to be. Now, there are solutions to this kind of thing in CG that already exist. There's the very popular bake it all out on twos and put it on step tangents. That has problems because, for one thing, an animator will have to save version up, bake, and version down for revisions. Another thing is that these types of step tangents, these are not very useful when it comes to generating motion blur, when it comes to doing simulations. So generally speaking, this is not an ideal solution. Another acceptable way to do it is you can hand off your timing, your drop framing to the compositor. And that works, that's a fine way, except for the fact that when you give the timing solutions to the compositor, you're taking the timing decisions out of the animator's hands where it belongs. So the challenge, roughly speaking, is we want to put our animation on twos. We want to use dope sheet mentality, and we want to do it in such a way that's non-destructive and pipeline friendly. So the time filter solves this challenge. It allows an animator to achieve drop frame timing interactively with no need to bake. And the way that it does this is it changes the way time is interpolated on select sets of curves. Right now we're going to watch a short video on how the time filter works and how it goes in action.
This is a demonstration of the time filter system. Time filter is a tool that allows animators to manipulate time on certain sets of objects. There are a few different types of filters available. We're going to be taking a look at the drop frame filter and the time warp filter. The drop frame filter, for lack of a better explanation, helps you put your CG animation on twos, or more accurately, time out your animation on ones and twos. The standard method of doing this, you probably grab your whole rig and bake the curves on every other frame with step tangents. That's okay for some scenarios, but it's incredibly destructive to the animation process. The time filter affects time in a non-destructive way. Your animation curves are unaffected. So here's a simple example. We have a ball moving from point A to point B. Let's put the whole thing on twos. What we'll do is we'll create a drop frame filter, and we'll say the hold will be twos, and hit OK. And now we see in our time filter window, we have a new filter called ball, and inside this ball filter we have our object here, P-sphere. And if we play the animation, we can see that although its animation curve is unaffected, it behaves as if it's on twos. It doesn't have to be on twos, you can put it on fours or tens, whatever you like. We also have the time warp filter, which works the same way as the Maya time warp, except it applies only to the objects within the filter. So let's make one of those and put that on the cube. We'll call this one cube. Now we see that we have this new curve for our time warp, and let's show you how this works. Drop a key in there, and there we have a time warp on just the cube. So we can see two different objects with two different time filters and how that works. Now let's try a more advanced example. So here we have a nice little scene where Froggy is jumping through the air, and I want to put a time filter on this to punch it up a little bit. I want to put the slow parts on twos and the fast parts on ones. So the first thing we're going to do is we're going to create a new filter. I want a drop frame filter. Now we have a drop frame filter with nothing inside of it. I want to put the entire Froggy rig inside of it. And the way to do that is I'm just going to choose any part of his rig. I'm going to right click on the add button and I'm going to hit add all to filter. It looks like that worked fine. So to start with, I'm going to say I'm going to want him to be on twos at the beginning. As he enters into his run about here, let's have him go on to ones. Okay, that's looking good. And as he jumps into the air, as he reaches the height of his jump, I want to put him back onto twos here. And now we get into the main issue with a drop framing in 3D. So if we go to the perspective view, we can see he is on 2s. He is indeed on 2s on these frames. But if we go to the camera, well, the camera is moving, so he's not holding still for 2s. He's stuttering. He's strobing, because while he's holding still in world space, he's not holding still in camera space. So we want to fix that. And how do we fix that? Quite simply, we take our drop frame filter and we hit this button here, which is the Create Camera Offset. And you'll notice that we have a new little, it's opened up a new window. There's a new node there, which is the Froggy Camera Offset. Now, when we scrub, he sits nice and still, as we expect him to be. Okay, so he's going to come, as he comes down in this fast part, I want the filter to go back onto 1s, especially if he's interacting with the ground. I don't want him sliding on the ground. And this is the point. You give the animator control over when he's on 1s and when he's on 2s. You don't want your character to be sliding on the ground. And that is all we have to do to put a drop frame animation on our character.
So I'm going to talk really briefly about what it means when a camera offset is added to a filter. When you add a camera offset to a filter, the constructor creates this string of nodes here, and what this does is it takes the camera matrix and the modified time as inputs, and it outputs transform data. This is the formula for the camera offset matrix. I sorted this out in Maya through trial and error by wiring and rewiring strings of matrix nodes. My supervisor, Gaetan, sorted out the math after the fact. He's much better at this stuff than I am. I would not be able to solve this mathematically if my life depended on it. So we had to add to the rigging pipeline with the advent of time filters when we create an asset at Marza. If the project has filters, then every asset will have a camera offset node somewhere in the hierarchy. And what that is basically is just a node which moves the entire rig as a whole. When a camera offset is added to a filter, the system searches the filter for all of the rigs within it and for all of the offset nodes within them. And if an asset doesn't have a camera offset node, then the user can provide one. So with the time filter system and the camera offset system working in tandem, we solve the drop frame timing problem interactively, non-destructively, with no need to bake, and complete control over camera space held frames. But this was only the beginning of the problem. On a typical animation workflow, when the animator pushes the Publish Scene button, the pipeline takes over, publishes animation, publishes camera animation, sends it down the pipe to be reassembled for other departments, lighting and special effects. For a project that has time filter, well, what we did was, I went back in time. We created a new class of publishable, which is the time filter data. You can see what that kind of looks like here. So if a project has time filter, then when an animator hits publish, anim gets sent out, the camera gets sent out, and the time filter data gets published alongside the animation. So a scene can be reconstructed with modified time for simulation, for lighting, and for rendering. So time filter accepts anything that moves, including cloth, fluids, particles, you name it. You can take your cached geometry and stick it into the scene's existing filter, or you can duplicate the filter and make tweaks to it for such cases where the simulation timing only needs to mimic the animation for portions of the scene, but not all of it. So the point is that you can use, not use, or partially use the filter. That choice is up to the animator. You can add a camera offset to simulated geometry too. The process for doing that is just you create a group, you put your simulated nodes into a group, and then you tell the system that that group is a camera offset node. I want to touch just really briefly on importing and exporting because that turned out to be an unmitigated headache. To get one-to-one results at the different stages of the pipeline, we had to solve for filtered nodes that were constrained to unfiltered nodes and vice versa, and solve for every possible permutation of a node which can be considered to be in multiple filters. So what you see up here on the screen, that is just a small fraction of the logic that went into publishing, importing, and exporting filters. So, drop frame timing, that's just one way an animator may wish to tinker with time in a scene, and as such, the drop frame filter is only one of the filters that are available in the system. The other most popular filter is the time warp filter, as you saw in the video. And every filter comes with an optional feature, which is the stagger feature. And what that does is that shuffles your drawings in the traditional sense and gives your animation a staggered interpolation. I'm really rather fond of that feature. So these days, Time Filter is a standard tool which is used in pretty much all the animation projects we have at Marza. But getting here meant we had to solve the final challenge, which was getting the animators to actually start using it. And we did that with the help of our key animation staff, who were vital in providing the feedback that we needed to create the most user-friendly experience possible. So this, you can say, was the social engineering portion of the task. And on that note, I'll say that it's important, it's always a good idea to be willing to bridge the gap between creative and technological teams. And that's always been a bit of a challenge in the CG business. But I think that's one of the hidden strengths that we have at Marza. So where are we now? Of course, we're updating to Python 3. We've closed the book on user requests, and we're in the process of abstracting the GUI, because up until now, it's been a very Maya-centric tool. But we are we're recreating the core function providers to support the major packages like Blender and Houdini. You can see the time filter running in Blender up there. So that's where we're at right now with the new team. So the system in its entirety is not publicly available yet, but it's my hope to have it all up there as an open source project very, very soon. In the meantime, all of the instructions and all of the formulas for creating a time filter of your own are available at the link you see on the screen, which is marza.com/timefilter. So putting animation on twos and holding drawings to camera space, that's just one part of achieving the 2D aesthetic. In the end, it takes a marriage of multiple departments and a solid understanding of animation fundamentals. And a time filter, this is one tool in a vast arsenal. And some might say that it is neither novel nor vital. But I like to think that with the time filter, we've come a little bit closer to putting that old-fashioned animation timing style back into the hands of the CG animator, and opened up new areas of timing that have yet to be explored. Now, I want to thank Gaetan Guide, Kim Sol, and Stéphane Mangin for their help in building the time filter system. I want to thank Shashwat Brahmbat, Matsunari Takamasa, and Sergei Morozov for their help in building the extended features, to Mayumi Tachikawa, Alina Kordesh, and Hiroaki Mita for their unwavering support and help in getting ready for this presentation. I'd like to thank the extremely talented Greg Court and Heike Manukan for allowing me to use their animation for this presentation. And finally, to Susan Reiser, Stephen Spencer, Ala Sheffer, Nora Wixom, our chair, Shiranjit Mandal, Barbara Ryan, Mandy Adland, and Mark Montague for accepting my paper, for teaching me how to write a better paper, for always being available to answer questions, and for making it possible for me to be here to speak to you today. Thank you very much. And to all of you for listening, thank you very much.